Okay, so we're going to talk about inelastic collisions as opposed to an elastic collision. An elastic collision is where you would bounce off, like a couple of rubber balls bouncing into each other, right?
Yeah.
An inelastic collision is where the things come together and they stick and they don't separate. Okay, and as an example of that, consider a bullet fired into a block of wood. Okay, so initially the block of wood is at rest, the bullet is in motion, and afterwards the bullet is embedded inside the block of wood and the two move together. You see?
Yes.
So let's set up our conditions, right? What is our, well, let's write down what these numbers are going to be. Our mass will be equal to 10 grams, which is going to be 0.01 kilograms. And the velocity, the initial velocity will be 1,000 meters per second, which is a very fast bullet. Okay?
Okay.
So what conservation of momentum, right, is what we're going to use here. Okay?
Okay.
Because conservation of momentum tells us that, I'll put it up here, that P final will be equal to P initial. Okay, that's the final momentum of the system, of the bullet and the wooden block, will be equal to the initial momentum of the bullet and the wooden block. Okay? So initially, what do we have? I guess I need a mass for the wooden block here as well. So M2 we will set to be 490 grams, or 0.49 kilograms. Well, so initially, right, P initial will equal, say, P1 initial plus P2 initial, where that's the momentum of the bullet plus the momentum of the wooden block. Well, the momentum of the bullet is the mass of the bullet, m1, times v1, the velocity of the bullet. And the momentum of body 2 is the m2, mass m2, times the velocity v2. But I said that the block is not moving initially, so this will be 0. v2 will be 0, so this term will go to 0. And so our initial momentum, we'll find, is just equal to m1 times v1, which is 0.01 kilograms times 1,000 meters per second. And that will be equal to, I think, 10 kilograms meters per second. So that's our initial momentum. Okay? There are no units of momentum, like official unit, like newtons or something like that. You know, it's not Galileos or something. So standard units, though, will be kilograms and meters per second. Okay?
Okay.
Afterwards, what do we have? Well, P final is going to be, it's the same as before, it'll be P1 final plus P2 final. But since these both have the, this will be M1 times V, they'll have the same, or V sub S. They both have the same velocity because they're moving together, right? So that's M1 times V sub S plus M2 times V sub S, which is just equal to M1 plus M2 times V sub S. And M1 plus M2, that's 490 grams plus 10 grams is 500 grams. That will be 0.5 kilograms times V sub S. Okay?
All right.
We don't know what V sub S is, that's what we want to find out. That's why I put the question mark there. So we're going to solve for that, because that's the unknown that we have. Okay? We can solve that using conservation of linear momentum. We set the final momentum, which we have here, 0.5 kg times V sub S, equals the initial momentum, which was 10 kilograms meters per second. 10 kilograms meters per second. We can multiply both sides by 2, and that will give me V sub S equals 20 meters per second. So it's a pretty quick moving block. Okay?
Okay.
So all I did was just solve for V sub S by dividing out 0.5 kilograms from both sides, right? And that left me with 20 meters per second is the velocity of the block and the bullet moving together. Okay?
Okay.
And that is an example of an inelastic collision. Okay? Does that make sense? And
Yeah.
and we solved it using, conservation of momentum.
All right.
It's probably worthwhile for you to think about how would I have solved this if I did not know about conservation of momentum, right?
Okay.
You probably would have had to make some assumptions about the force that the bullet applied to the block, right? And we don't have any details regarding that. We didn't even need them, okay?
All right.
Now this is, of course, assuming that there was nothing lost. This is an idealistic number. In reality, the speed would be a little less than this because it would take away some of the energy that the bullet had, and energy is something we haven't talked about yet, but some of the energy the bullet had would have been lost to the heat, the deformation of the wooden block, because it takes energy to do that, and some heat that would be generated, right, as it slid into the wooden block, okay?
Okay.
And so that energy would reduce the velocity of the system that resulted afterwards. But again, we haven't got to energy yet, and once we do, we will use it to deal with different collision problems. Maybe we'll do some, more complicated collision problems, but I don't know that we will.
All right.
But we'll certainly do elastic collision problems, which will need energy. We'll have to talk about energy first before we can do that. All right, well, I think that's it then.